I'm just going to talk a little bit about PCB design. You can go to conferences for days and days about PCB design. I'm not trying to cover everything. This is just a few little things that people often don't think about and are easy to think about and might well improve your PCB design. So a little bit about me. Oh, if I move to the right slide, there we go. Who am I? Well, I've been an electronics engineer for nearly 30 years. I grew up with the BBC Micros and I made all sorts of add-ons for my BBC Micro over the time. EEPROM emulators, I made quite a few of those. I think I even sold some of those. I progressed to go into university. I have my master's from York University. And then I went off into the big bad world of designing boards. I did a lot of early stuff, designing systems with FPGAs and CPLDs. Moved on to working for consultancies. And consultancies are fun because you get to do all sorts of different jobs. So one job one week is maybe interfacing to something particularly agricultural or something, and then the next job next week might be something entirely different. So you get to do all sorts of things. And so with my job over the time, I've been doing various boards at various speeds. The fastest board I did was a board which had 20 gigabit serial links. So a 20 gigabit serial link over a half-meter bit of cable. The cable actually, the data is going so fast that the cable actually contains data. You get more than one bit of data in the cable. In fact, it's about 4 to 5 bytes of data in a half-meter piece of cable. There. So I had many years away from IB, but over the last 5 years or so, I've got back into designing add-ons for the BBC Micro, mainly around the Raspberry Pi. So a common thing I hear is, why do I care? I'm only using a 1 megahertz clock, so my PCBs can be made in all sorts of random ways. 1 megahertz clocks, well, the actual base frequency is slow, but the dominant thing is actually the 1 megahertz actually specifies just how often the signal edges occur. And it's the signal edges that contain all the high frequency. So even if we go back to an old 74LS00, these chips have about a rise time of about 15 nanoseconds. And that means the third harmonic is at 200 megahertz. And now lots of people like to try and keep the fifth harmonic to keep a square wave looking reasonably square. So you're going even faster. So even with an old 74LS chip, you actually have quite a lot of high frequency energy going around. And if you're designing using newer chips, FPGAs, CPLDs, some of these chips have 1 nanosecond rise and fall times quite easily. And that can present problems. And even though you might think you're just using a 1 megahertz clock, it's the edges that are important and the edges that give you the energy. So what can happen if you don't pay attention to your board? Well, the biggest thing that can happen is it just radiates and interferes with radios and TVs. And the old BBC Micro, if you have a radio near it and you tune it to the right frequency, you can hear your computer in the radio spectrum. Now, you might not worry about this, but maybe your next door neighbor might worry about it. Officially, you probably ought to start thinking about CE and FCC compliance, though I'm not going to talk about any regulations and stuff like that because that all becomes quite complex. within your world, the signals on the board become distorted and even corrupted and unreliable. And this can be a real problem when you have to diagnose glitches, double clocking and timing issues, especially if you don't have high-speed test equipment. I'm lucky I have access to a lab with some very high-speed test equipment, and I can go and look at these edges and check that they are nicely formed. And glitches and double clocking, especially with fast FPGAs, the FPGA may well see 2 clock edges quite easily on a signal, and that can give you problems when you're trying to diagnose what is going on, why a counter clocks sometimes 2, sometimes 3 times for every clock edge. So I'm going to talk a little bit about loop area. This is something that is often not considered at the lower end of PCB design, and really should be. So what do I mean by loop area? Let's just say we have a single-sided PCB here, and we have a ground track, and then we have a signal track, and it's managing for some reason to take us a strange path around the board. And if we just say the sides of this square is 10 millimeters, we have an area of 100 millimeters in there. Now, that is huge. If we have to have the signal going around this path, if we were to take the ground signal around the inner side of that path as well, and if we did some simple maths, I'm just going to round things. We said each side of this edge was 10 millimeters. So the area between the ground and the signal, if we follow the inside track there, and we have the track spaced at 0.2 of a millimeter spacing, we end up with an area of 6 millimeters. That's compared to 100 millimeters. So that's a significant difference. Now the energy actually flows, well, actually, no, let's not talk about that quite yet. I'll come on to that in a minute. So this is another common thing you might find on a single-sided board. You've got a bus that goes across the board, and you've got a ground track that's somewhere there. So you can see the area between the D0 and ground is nice and small, but it's getting worse and worse as we go up. So D1 is bigger than D0, and all the way up to D3. The area from the ground to D3 is large. Within the same amount of space here, if we shuffle the tracks around and we put the ground track down the middle, what we've got is that both D1 and D2 then would have the smallest area, and D3 and D0 would be having slightly bigger areas. So we have improved our loop area. Whoops, don't go too many slides. Even better, if we can go ground, signal, ground, we then get a really small loop area for our ground and our signal traces. Now, if you've ever looked at the wiring of the user port, for instance, on the BBC Micro, you'll see on the ribbon cable, it ends up as ground, signal, ground. And that's because it keeps the loop area down, which keeps the noise down and keeps the signal integrity up. Now, decoupling a chip. I've got some surface mount packages here, but these could easily be through hole. You can see electrically, we've connected both the ground, which would be pin 10 on this chip here, and the power, pin 20, to the decoupling capacitor. But we've got a bigger loop area here. We can do better. If we move the track here, we've got a much smaller loop area. And so that produces better decoupling. If you've got a double-sided board, sometimes you have traces that have to duck under to the bottom layer and back up again, because you've got other traces on the board that go vertically. So you can take a ground down and around, and that keeps a constant loop area for this trace here, this trace that ends up going across, starts at the top, goes down through a via, goes across, and then back up again. if we didn't have this ground that we moved here, then the ground of the loop area may well be going right off the top of the board and around, and then we might get some of our bigger loop areas that we saw before. So you can do exactly the same as we saw previously. You may well think, oh, I've got another layer, I don't still need to worry about loop area. Well, the loop area is still important if you have a 2-layer board, and sometimes you can just move the wires just slightly, and you can see here we have an even smaller loop area. And this all helps with keeping the impedance down and the signal quality up. Decoupling capacitors. People often, I see this quite a lot on boards here, and what we end up with is a huge loop area to where you're trying to go. Even if it's just down to the planes, if you're doing a big board with multiple planes, you end up with a big loop area. But you can do better by putting the wires very close to the capacitor. You can do even better by putting side by side if you do the maths here on the loop areas. And the loop area is important. You have to consider the 3-dimensional side of the loop area. I'll come on to that in a second. And you can do even better by putting 4 wires on your capacitor. Wires often are almost free in circuit board design these days. So here we have 1 loop and 2 loops. So we have 2 loops in parallel, and that actually means we have a much lower impedance for the wire placement and the decoupling. So we get better frequency response. So here is a picture. We've seen something similar, but this time, let's imagine we have a ground plane. So we've got it in green. And we have a signal coming in here on the left-hand side, signal going out. And again, the track, even though it's got a complete ground plane, runs along the top and back down again. Now, a lot of people will think the energy will flow along the top, along the trace, and back out, and then return through the ground plane in a straight line. Well, actually, the energy doesn't. You'll find the energy will take the lowest path, the lowest loop area path, and actually the lowest loop area path will be in the ground plane here, if the ground plane is close. So let's say the ground plane is 0.2 of a millimeter away from our trace. If we do just the center bit like we did before, if we say the sides and the top are 10 millimeters, or I know it's not quite, but I'm just doing some approximate maths here, we would end up, if you think the area is 100 square millimeters, actually it's not, because the current, the high frequency current will actually flow in the ground plane under your trace on the board here, because that's the lowest loop area. So under here, if the distance between the top layer and the ground plane is 0.2 of a millimeter, and we just say this trace is 30 millimeters long, we end up with only 6 millimeters of loop area. So this is sometimes counterintuitive to people. Lots of people think it will flow through the quickest path, and at DC it will, but we're talking high frequency here. All the edges, all the high frequency energy flows under the trace in the ground plane. And so there won't be any high frequency energy at this point here in the ground plane. I've just explained all of that. So the simple maths, the signal trace times the length of the signal trace times 2, because we've got to go there and back again, and the distance between the trace and the ground plane. Right. And now just a simple little slide here. Just because you can route your traces nice and close to your through holes, as this person here has done, this was my little example earlier, doesn't mean you should. It would be better to try and keep the trace spaced away here. Because what often happens, especially on low-cost PCBs, is the solder mask, which on this board here is defined by this little yellow ring here, this little very faint yellow ring here. The solder mask at the edges is often of slightly poorer quality and is easy to damage, especially when soldering. And that's where often shorts will occur when hand soldering circuit boards. And so for the hobbyist market, where you're sometimes hand soldering through whole parts, it would be better to try and keep the track as far away from the through hole as possible. So I have whizzed through my little simple thing here about keeping your loop area small. And so the big thing here is, just because you're using a 1 megahertz clock, 1 megahertz clock is slow, but it's the edges that are important. And the fast edges will want to take the smallest loop area. And if you don't provide a small loop area for them, they will radiate. And this is also important if you're trying to probe high-speed signals with your oscilloscope. The loop area, as again, includes the earth lead, that big flexible bit of copper, not copper, crock lead here. And where's my camera here? Here's a scope earth lead, and you can see it's 4 or 5 inches long, and that will affect the signal quality. Often on the end of the oscilloscopes, you have a little earthing ring. If you can get a little bit of tin copper wire, wrap it around there, and you can get your loop area right down, you'll have an increased signal quality. You can add extra ground tracks if you have space to give you a return path. And that really helps. Think about the wire placement and make sure it is, try and keep the energy as short as possible to keep your area as low as possible. Sorry, I muddled that up. There's a few I've made a few simplifications here just to keep the presentation short and quick. So there's lots of time for questions, and that's it.
Hello, it's Andy here. Can you hear me?
I can hear you, yeah.
Can I just ask, regarding like FPGAs and CPLDs, is it always then therefore best to keep your slew rates as slow as possible for the sort of boards we'd be making?
Absolutely. Really do try and keep your slew rates down. It really helps your signal integrity on the boards. Absolutely. The only time that you might have to sneak up your slew rate is if you have a timing issue with the signal coming out, that you need another few nanoseconds of time. But so slowing the slew rate down on FPGA may go from a nanosecond to 5–10 nanoseconds of slew rate, and that really helps with the signal integrity. So you're now moving your signal down from gigahertz edges, radiates really high up in the frequency spectrum, down to maybe only 100 megahertz, 200 or 300 megahertz. So, and that really helps, because if you really want to design really good boards, you spend time trying to make sure that the signals are terminated properly. And so all that energy that you've launched down your track doesn't get reflected and continue reflecting and bouncing up and down the signal trace. And that termination can often be hard on the levels of boards we're sort of dealing with. So yes, turn down the slew rate.
Okay, great, thanks.
So I've got a question. Would I be able to share my slides on Stardot? Absolutely, yes, I can do that. Everybody must be happy. Excellent. Oh, no.
I've got one. Sorry, I missed the start of that, Dominic. Would you be prepared to do a future one on PCB assembly? Because that's, I'm going to watch back what you've just done because it looked really interesting. I've never done PCBA stuff yet, and I have no idea where to start with it.
Yeah, I can consider that. I cheat these days. I mean, I do a little bit myself, but through my job, I mostly get my I get all my boards assembled on big surface mount production lines. But yeah, I can try and do a little bit about that.
Cool. And then another one, just
certainly.
Do you know anything about when you're doing FPGAs and CPLDs? If you keep the slew rate down, do they tend to not work if you just do a two-sided board, or do you really need a 4-layer board for?
You can do CPLDs and FPGAs on 2-layer boards, but the real thing is to try and keep the signal integrity up. If I can share, if I just get another PCB open. On my computer, I have so things like if you have spare pins on a CPLD, what you can do is make the spare pins ground pins. So you can set them up in the CPLD world to be to drive to a 0, and connect them to ground. And then that will give you another trace to get a ground signal effectively out of your CPLD and along your board. So really try and keep your signals, as many ground signals going between your source and destination, because that will help keep the loop area down and the signal integrity up. And have a think about how the signal is flowing. A lot of people forget that the signal has to flow back through the ground somewhere. So try and think about how the signal comes back, especially through the ground path. And this is even more important for clocks and things like that, because the edges of clocks are very important, because you end up clocking flip-flops and things like that. So if you have a poor clock edge on a flip-flop, you may well get 2 edges of the clock. And then that will really potentially really corrupts counters and things like that. So try and think about how the ground is flowing and how the return path flows. And sometimes you'll find just simply putting 1 or 2 extra wires in a circuit board will massively reduce the ground return path on a 2-layer board. And that can massively improve the signal integrity.
Are we literally saying solder all the unused pins to ground? It doesn't go ground through the FPGA itself. You're saying solder it to the board.
If you don't need them, solder them to the board, and in the Verilog and the HDL, assign them to 0.
Right.
And those pins you can assign to a high slew rate, because they're never actually clocking. But what that does is, and this is especially useful on a QFN package, what that does is it gives a nice return path, even through the FPGA, because the FET is turned on. And if you've got the high slew rate, what is happening is it's turning on all the FETs internally, because what they do often to do the slew rate adjustment is have multiple FETs in parallel. And then so that gives you a nice low impedance path into the substrate. And that will help with the signal integrity. So if you can do that, especially by a clock pin, then that clock pin isn't then going to affect the next pin beside it, because there's a ground.
Sure. Okay.
So so solder them and drive them to 0, and that will give you a nice low impedance path into the substrate.
Okay, great. Cheers.
What do we think of a 4-layer board? 4-layer boards. 4-layer boards are great because often you can have a solid ground plane. Sorry, this was a question on the chat. But there's some things to think about on 4-layer boards, even with that. Imagine you have a bus, 8 signals that are going across a 4-layer board, and somewhere they need to turn and go through the board down to the bottom layer. And so you have a row of wires. What that row of wires can end up doing is causing a slot in the PCB. So you need to think about perhaps just adjusting how the wires are placed, and don't place them all in a straight line, so that you actually can break that slot into 2 perhaps. And so you have 2 little slots with some ground in between. And that will keep the ground plane flowing a lot better there. 4-layer boards is another whole, it is good and does have a massive improvement. But there's lots of things that people still need to think about with 4-layer boards. I've managed to turn off any clocks. So often a 4-layer board will have the top layer being a signal layer, the next layer down being a ground plane, and the bottom layer being the next internal layer being a power plane, and the bottom side being tracks. That's a good stack up. That works for lots of things and lots of people. But when you're transitioning between a signal between the top layer and the bottom layer, what you're ending up doing is changing the reference plane. So on the top layer, the reference plane was your ground plane. And then on the bottom layer, your reference plane is now your power plane. So I was talking earlier about trying to keep your signal and a signal close to a ground. Well, this was slightly one of the simplifications I made. You can use the power plane as your reference plane. But what you need to do is to try and keep things nice and well bonded together. So in a PCB, in a 4-layer PCB, the gap between the power plane, the ground plane and the power plane will form a little capacitance. And that's very useful at the very high frequency. But at medium frequencies, 50 megahertz, that sort of area, 100 megahertz, you don't get very much capacitance. So when the signal is transitioning between the top layer and bottom layer, what it will typically do is go hunting around the ground and power planes for a decoupling capacitor to go up. So the return path signal will typically try and find, and it may well use multiple, well, it will probably use all the decoupling capacitors to transfer between the two. So what often people do on high-speed boards is actually have an extra capacitor right by where the signal transitions between the top layer and the bottom layer. So it's transitioning between the two power plane, between the ground plane and the power plane. Does that sort of make sense, is what I'm trying to say there? So you might add in some extra capacitors, which will help with the decoupling as well. But what sometimes people do is actually change their power, the planes stack up so that the two inner planes are actually both ground planes, and then just have an extra ground wire to link the two planes by where the signal transitions between the top layer and bottom layer. This is probably all much better explained with some pictures. So if people are interested, I might do some, I can do a next one on 4-layer boards and stack ups of 4 layers and 6 layers. 6-layer boards are becoming much cheaper these days as well. So I've got another question. Is it okay to run a bus line as close as possible together, or could this cause crosstalk? Well, rule of thumb, and this is a rule of thumb, if you can space your signals apart in the ratio of 3 times the distance between the signal and the reference plane. So if you've got a 4-layer board and you've got a ground plane, and that's say 0.2 of a millimeters apart, 0.2 mil between the signal trace and the ground plane, then you should have the tracks 0.6 of a mil spacing. And that keeps the crosstalk down. And I can't remember the number of the figure off the top of my head. It might be less than 1% or something like that. I would go and check if you're particularly worried. But that's the general rule. And of course, the art of PCB design actually on high density PCB design is knowing when you can sneak a bit of rule 1 and rule 2 or rule 4 or rule whatever to try and make everything fit, and where you can compromise. Because all the examples everybody gives are total idealistic examples. When you actually come to do a board for real, there is no way you can sensibly, within cost constraints, deal with all of the constraints all together. But if you know which constraints and where you're compromising, then if you do ever have problems, those are the first areas you can go and have a look at.
Could I ask another quick one?
Certainly.
I don't know if you'll be able to see this. I've got a board that I was messing around with. It's a network board, which
Right.
kind of works, but it uses one of these WizNet modules, and it's really fussy about the read and write select clock edges. And if there's any ground bounce or anything like that, it double selects and tends to skip a byte. So you can see on here there's a load of bodge wires and bits of solder braid that I've nailed to the bottom to try and improve things. The problem I had with part of it was there's like two ground planes separated by a load of wires, so I just ran out of routing space. And it goes from one side of the board to the other and back again. So the return path was quite tortuous getting around this area. Would it have been sort of, I don't know, a kosher sort of way of doing it, of just putting a whole bunch of wires in instead of one or two to increase to like reduce the impedance when you're transitioning from one side of the board to the other? Or is it a real bodge?
No, people do all sorts of things. So when transitioning, so did you say you had two internal ground planes?
No, this is two-layer board. So there's a ground plane on like the top side where the components are, and then there's two ground planes on the bottom that are separated by, I think there's like 3 tracks go up there. So I've bodged it with a piece of braid from one to the other to decrease the impedance.
Yeah.
Would it have been better to just put more wires between those two? So I think, you know, there's a bit of bounce coming from the bottom plane going to the top plane and back to the bottom plane. I just put one wire in for each transition. If I put like half a dozen, would that have probably improved things?
It can't do any harm. Wires are virtually free these days. Very rarely does the PCB manufacturer say, oh, look, I'm going to add you an extra 10 cents because you put too many wires on your board. So don't skimp on wires, is what I would say.
What about bigger wires versus smaller wires? Do bigger wires have any sort of advantage in terms of, you know, there's more gold or older there?
They do and they don't. Often the bigger wires actually then force your actual signals to take slightly longer paths. So it probably doesn't make a difference. It's probably having a good bond along the planes. I mean, I'm quite happy if you want to actually bring up some CAD images on the screen, and we can chat through it either privately or whenever.
No, this is a general question. I actually fixed this problem in a different way. It was actually, I can't remember what I did in the end, but it was, I think I just slugged the signals with a bit of capacitance.
Yeah.
And actually, it was just any noise on those signals as it was transitioning was causing it double clock. It's a known problem with these modules. I've kind of given up on these. They're a pain in the ass generally, but they're really, really fussy. But no, it's just a general question on wires. I wasn't sure if the real tiny micro wires will better or worse in any way for signal integrity.
I mean, you can spend literally tens of thousands of pounds on getting programs that will simulate how a wire performs, and actually a lot of this, a lot of what people actually do these days is they will do 5 or 6 test boards and then measure them, because sometimes a lot of the old rules of thumb and theories don't actually stack up in practice. And some of these analysis software is getting a lot better, but they are costing tens of thousands of pounds just to analyse how wires and how signals flow on circuit boards. And you know, they are needed these days with people going faster and faster, these very high-speed memory interfaces and things like that. So, yeah, usually it's more, two little wires is usually better than one big wire.
Yeah. Thanks.
Dominic, can I make a suggestion? And do please feel absolutely free to say no if you think that this is a bit much. but I wonder whether you would be prepared to do a second session at a later meeting, perhaps, and we'd have to think about how this would work, in the form of a clinic in which in advance we might send you 2 or 3 designs, probably so far as everyone else is concerned, anonymously, and you could identify what you think are the good points of those designs and what you think are perhaps the weaker points of the designs. I don't know whether that would be something you'd be prepared to do.
Yeah, I'm prepared to do that with the caveat that sometimes things might well be subjective, and I'm prepared to do that. Yeah. I do review stuff. I've done it throughout my life, reviewing designs, and that includes circuits as well. But yeah, no, quite happy to do that.
That would be really great, because there seems to be so much material online about how to actually use the software, you know, how to place a via and how to, you know, switch thermals on and off and how to make your vias tented and so forth, but not necessarily telling you what's a good way of doing it. Yes, that would be really helpful.
I will say good actually depends, because you may well have other constraints. So this is where the examples on the internet, you know, they all have the idealistic way of doing something, and actually when you come to try and juggle the 30 signals you're trying to do this and the other bits and pieces on the board and the shape and everything like that, it's all about compromise. So yes, yep, quite happy. We'll have to work out how to arrange that, but yes.
Yes, I mean, it would be, I mean, I suppose there'll be various issues, including what CAD software you use, because everybody seems to be using something different. So there's people using Eagle, there's people using KiCad, there's people using Easy EDA, which all have their quirks. And somehow you're going to be able to need to show these designs on screen and point to things, but we can think about that.
Yes, I will say all CAD systems have quirks. I use professional CAD systems. I've used lots of them, and I don't think I know any PCB designer that doesn't swear at their CAD system at some point.
I started off using Eagle, and in terms of sort of the mechanics of just using the interface with all of its annoyances, I just know how to do it now. And I simply won't move on to another platform. And I know that I have to pay for my Eagle because I go beyond the limited free board sizes. I just can't face the idea of having to learn how to do all that again on a different piece of software. And one of the things I do pretty much with all the boards now is I design my own footprints. I don't use the footprint libraries. And that's a tedious exercise in any software, and I can't face learning it in another. But I'm sure there's some way that we can, you know, maybe using a Gerber viewer or something as an alternative to the software. But that would be great if you could do that. And I think Ed has just posted up a link to a useful thread on the 6502 forum, which I think should be everyone will be able to see that. Thank you very much indeed, Dominic. That was an awesome talk. It was really helpful to get some insights into professional PCB design and the kind of things that we should be doing. I have to say, my own experience is my boards tend to fail for far more fundamental reasons, like having the diode the wrong way around.
It happens. It still happens in the professional world.
At the moment, I'm trying to work out why the output from my buck converter is 0 volts. I don't think that's due to anything subtle.
No,
it's just not switching at all. Anyway, thank you very much indeed for that. I don't know whether people know, but in the bottom right-hand corner of the screen, there's a way of applauding people who have given talks. Yes. A few people have spotted that. So thank you very much indeed.